Okay, thank you. Does this work? Yeah, okay. All right, so we're gonna talk today about measuring complexity. There was some things in the keynote speaker about measuring complexity when he compared, for example, the different areas within the Roman Empire and their varying levels of complexity. So the question you have to ask is, how in the world do you measure complexity? And the question here is, can it be done with any precision and reliability? And that's the problem, as we'll get into. So is difficult to measure. Just even think of something simple like a geometric figure. If I ask the question, what's the longest figure? You'd say, well, do you mean circumference? Do you mean this widest diameter? Longest line. What do you mean? So with complex systems, we're talking about something much more complex or complicated than a simple geometric figure. So answering the question is not always immediately obvious. So Seth Lloyd is from Santa Fe Institute. He's a physicist. He works at MIT as well, and he has taken the trouble to try to list the number of ways of that complexity has tried to be measured in the past. Now, outside the world of big history, really energy rate density is not used, at least not that I've been able to find. And when I contacted him, that he had left out Eric Chazon's, we're going to talk about later, metric for energy, he indicated he was not aware of it. And unfortunately, he did not subsequently add it to his list, which there's a link at the bottom there that has his listing of over 40 different metrics for complexity. But he divides those 40 some into three main categories. And of course, we have the additional one with Eric Chazon, who is one of the pioneers in big history. So measuring the amount of information is one of the first things, and it's the most intuitive because complex systems, as the last speaker just indicated, is really the amount of information. Energy is certainly necessary, a prerequisite for complexity, but complex systems themselves are not energy. They're composed of different atoms in certain degrees of order. And information, syntactical information, is essentially what is the relationships or ordering of different components in some way. So at least that's what it is if you want to get to the physical level. So the opposite of information in the universe would be the cosmic microwave background. There's just photons floating out there in space, and there's really no order to them. So that's ultimate chaos. Whereas without information, you would not have structures and processes. So, measuring the content can be estimated and approximated very roughly. But from simple systems, it's more doable, but as you get more and more advanced, it just becomes impossible, as Eric Chazon does point out as well, and everybody else essentially. So, essentially, we tried to say, well, how much information is in the sun? You just throw up your hands because there's so much interactions going on besides just kind of the number of atoms that are there. It's all the processes, the different kinds of atoms interacting in different ways and so forth. And that the sun's a relatively simple system, although it's huge. So measuring its content, you can imagine that if it's a very restricted amount of information, then you have things like crystals, which are not very interesting. And the opposite end, you have things that are not really relating to each other in any way except by collisions and so forth. And that's like a room full of gas, which is chaotic. So there's the information content of a complex system lies somewhere in between the strict crystalline structure of minerals and diamonds and so forth, and the extreme lack of relationships that occurs in a nebula or a room full of gas. We have to use statistics to say just some general things about it. So one description, there's a number of them that try to quantify a complexity by the amount of information. So one articulation of that was done by Andrei Kolmogorov, a Russian mathematician, 1963. And he said it was the shortest program that a Turing machine or a simple computer could print out that would then define that system. There's a problem with that though. So A simple, system might be just ABC, or represented by ABC, think of like a DNA. That's very easy to define. It's just ABC ad infinitum. A very short program can, print out ABC over and over. At the opposite end, though, you have chaos, and in Kolmogorov, uh, uh, algorithm does not account for the fact that when you get to a chaotic room of gas, um, it's really random. And now you need a program that's just as long as a string of information you have there, or a string of data, actually. So it's not helpful, so that's where it falls off. So Murray Gell-Mann, who came up with the idea of quarks and named it, and he was also one of the pioneers at Santa Fe Institute, came up with what he called effective information. So he's worried about the parts of the DNA, as an example, that actually do something, and it's not just random. So you might say it's the functional genes within the DNA versus the junk DNA. Of course, the junk DNA we're finding out might have more to do than just be junk. They might actually be regulating the other genes, and genes are hard to define. They overlap each other, etc. So that's part of the problem with the effective information idea, is that it is hard to figure out what part of a DNA strand or the ecosystem is just, it's just garbage. It's just there. So, you know, the fact that a peacock has a green feather, it might be just accidental. It could have maybe attracted mates historically with a red feather. So some information might not be relevant. Although its feathers in general apparently help it with sexual reproduction success. So again, complex systems are somewhere between order and disorder. It's a well-known property of complex systems. And what's important to understand, which makes it also difficult, is that complex systems are dynamic and they have a range of information that they can exist in. So we're all, in a healthy state, it's a constrained range of information that health exists in. As you get sick, the ways of getting sick is vast. And the information kind of falls apart, and when you die, you know, you're essentially going to chaos. So everything has to be in a certain relationship, but one of the other difficulties of measuring the amount is the fact that complex systems are dynamical, and from instant to instant, they do change. They're not like a crystal just there. It's a range of syntactical information, so it makes it daunting to impossible to estimate or quantitate complexity degree. In addition, of course, there's processes. So, you know, birds flocking together. There's simple rules that the birds apparently follow, that these incredible patterns fall out. Those of you may not be aware that they're at the Santa Fe Institute. Also, they've done things with lack of central control. There's just local atomistic control of rules of how one particle interacts with each other, and you can get some very interesting patterns occurring through matrices of these different agents. This is, I think, called a glider. John Conway's game of life is one where simple rules for each dot can serve as a model for how system processes can occur. Of course, on the level of life, the rules are very complex, both formally and just as common, simple understanding of complexity. So that also makes it difficult to quantitate how much. Now, another general way to measure information. Again, there's many other specific ways to measure the amount of information, but we have limited time. I can't go through all of them, and plus I don't understand necessarily all of them. But another way is how difficult is something to create. That makes so something that's more difficult should be more complex. So, you know, bacteria preceded amoebas, you know, eukaryotes, simple ones like amoeba preceded multi-cell, and so on. So it gets more and more difficult to create. And instead of using bits of information for the amount, you might use time or dollars or whatever to say that this is one way to measure information. And Charles Bennett, a computer scientist, came up with what's the shortest Turing machine, much like Kolmogorov, that could reconstruct the information of complexity. It makes sense, but then you have to be careful with some examples used in other places that, well, a computer chip has greater logical depth than a human because computer chips were not possible in nature. You have to have a human. So a human has to come on that's sophisticated enough to make a computer chip. So the computer chip must be more complex. Well, that can be saved by saying, well, computer chips are not complex. They don't fit a lot of the characters needed for a complex system. But that mistake is made by some people, in my opinion. You can't use computer chips just as complex systems. If so, then they're more complex than the human, which it doesn't. The final way that Seth Lloyd lists is hierarchy, and if you're familiar with Tyler Volk's book, Forks of Culture, he also uses this. But this was actually originally articulated by Herbert Simon, a Nobel Prize winning polymath. I guess he's a political scientist, but he did a lot of other things. And he wrote a very great paper in 1962 that described complex systems as hierarchies. So you go from quarks to atoms, to molecules, you know, to interacting molecules, eventually life, you know, simple life. It keeps going up to human society, if you would. So it makes intuitive sense. But the problem with this is that there's very poor resolution. So essentially, we don't have necessarily, if you take out our social aspect, more, as an individual human does not have more different levels of hierarchy than a chimpanzee, unless you want to somehow count our neural pathways in the brain. But that's not truly a hierarchy. It's actually a way that our neurons interrelate and the number of neurons. But anyway, the resolution gets to be poor. I think it has a lot of validity, but it's hard to parse also different systems. So can we say that New York City is more complex than a coral reef? Well, there are different types of complex systems. So it's another limitation to this type of quantitative of information. Quantitating complexity.
I think evolution is arguably one of the some most of history.
Oh, sorry. All right, it must be from my, I guess I didn't erase the audio trial. So Eric Chazon wrote the book, and this is one where many of us are familiar with, that talks about measuring complexity by using energy instead of information, which is information is a very squirrely concept. I think more and more people are understand it in the same way. It wasn't historically so. But energy is great because in science, we love to quantitate. It's measurable. We understand energy. And so he proposes that you use the amount of energy per unit time, per unit mass to reflect the degree of complexity of a system. And it makes intuitive sense because more complex systems have more things to keep in order. They tend to have more processes. So it makes some intuitive sense. And his graph seems to support this as well. On a very gross level, it's counterintuitive to me. I still don't get how the sun has way less energy rate density than human brain. But I won't argue with his physics. I'm not a physicist, and but I am going to pick apart, unfortunately, some of his arguments because I think some serious errors are made that also show the limitations of using energy rate density. So anyway, if you read his book, though, it seems that this metric is.
That the author admits that
I'm sorry, I don't know how this is happening. I don't see the audio file, but trying to go back and it's not listening.
Is that the author?
Sorry, I'm not sure how that's happening. So one of the first things to understand is that actually he's not talking about the free energy, which is the effective energy used by a system. He's actually talking about the total energy. He admits that in the book, although he does continue to use the term free energy rate. So the efficiency of a system is ignored. And it turns out that even other simple animals, a few like the shrew and the pygmy marmoset, their brains use the same energy rate as ours does, which most people didn't think would be the case, but when you look at these unusual animals, they have very energetic brains, but they're much smaller than ours. So obviously size is also a factor, not just energy rate density. Also, it turns out our heart and kidney uses just as much energy as our brain does. So there's a number of counterexamples that unfortunately show there's problems with this metric. There's also a very low specificity definition of complexity. So I mentioned computer chips. Now he defines complexity, and it's understandable given his book's goal that he does not restrict himself to living systems, but he wants to go from atoms and molecules. So essentially going from general systems to complex adaptive systems. So it's understandable given his task at hand. However, again, complexity is usually defined by a number, at least, of characteristics. And the fewer characteristics you require a system to have, the less specific. It's increase in sensitivity, it's a trade-off, but you're less specific. So now you end up including things like jets and computer chips, which again are not complex systems by just about anybody's definition. Jets they're not emergent. Engineers design them, they know what they're going to do. They're not indeterminate. Pilots know when they do this, it's going to go up or down or whatever. They can control it. And they're not self-organizing and so forth. Same with the computer chip. Now, there's also a problem. One of the biggest problems of this metric as described is there's a tautology. He essentially concludes that if something has a higher energy rate density, it is therefore more complex. You can't set a golden standard until it's proven against other standards as well as intuitive sense. So probably one of the most incredible counterintuitive examples he states is that computer chips, the Pentium 2, which was contemporary with the book being written in 2001, uses more energy than the human brain. Therefore, the computer chip is more complex. Doesn't make sense. And our brains are very efficient. Actually, if they try to measure the energy used in doing calculus versus just sitting there watching kiddies play guitar, the energy is hard to measure, the increase in energy, or writing a novel or whatever. And of course, our brains do many other things, self-aware, planning, memory. Besides, most of its energy is actually used to maintain itself and to hold electrochemical gradients. It's just comparing apples and Mustangs or something. So anyway, there's also some evidence of selection bias. He wants to say that our yellow sun is more complex than the galaxy as a whole. That doesn't make sense for two reasons. First of all, our sun is not a typical star in our galaxy. There's about 7% yellow suns, and there's about 75 to 80% red suns. And red suns have a energy rate density, according to him, by 0.1 units, where the galaxy on average is 0.2. Most importantly, stars are a subcomponent of galaxies. I mean, maybe there's some suns wandering out, stars out there between galaxies, but the vast majority within galaxies, it appears. And so therefore, really, red stars are more representative of a typical star in a galaxy. And more importantly, stars again are subcomponents. So I can't say a neuron uses more energy than a glial cell in my brain. Therefore, the neuron is more complex than my brain. I mean, the same sort of thing. This is puzzling to me. I don't know why he strikes out and says we're going to look at complexity of structure and function. Now you're changing your hypothesis, and you also have to at least define what you mean by complex structure and complex function. So he compares wood and coal, he thinks hardwood, softwoods, and coals, and they have different degrees of energy. He rates it to their molecular complexity. I think it's molecular. He doesn't really say in the text, but in fact, it's the number of hydrogen bonds per carbon. So it turns out natural gas, which has no structure, has a higher energy rate density than coal and wood. For some reason, sorry about that. Also function. He uses a text called by Vlad Smil, who did a lot of analysis of energy. And I don't know why Mr. Smil or Professor Smil came up with the idea that hand slowing requires more energy than chopping wood. I don't know where he got that. But because he uses that reference, it's counterintuitive. When you look at other sources, nobody says hand slowing is more energy intensive than chopping wood. Plus, he doesn't say how the wood is chopped. They're using an axe, a chainsaw, a saw. So it's you can't make conclusions. There's just too many questions about that. I'm not sure why he wandered into a different hypothesis. So essentially, complex systems are difficult to measure reliably in price and precisely. They're difficult to determine the information and the average energy rate. I think Martin Van Duyn is later going to do a lecture on energy rate densities of a whole number of systems. I read his paper and he edited it, and he did a remarkable degree of work. His work also shows many counterexamples to degree of complexity and amount of energy use. It's difficult to determine many systems boundaries and other problems. So coral reef has, nutrients and animals flowing in and out. Cities have energy flowing in and out. Are you going to measure the concrete of the city, the roads, at night? It goes on and on. And then purely physical, they have different types of complexity. So they're all tied together with different characteristics, but they can be entirely different. So a weather system is different than a bacterium, which is different than a giraffe, which is different than the internet or our immune system. So they all have things in common, but there's also vast differences. So for the foreseeable future, it appears the complexity of a system can only be estimated, best guesses. Best metric to use will likely depend on the context of what you're studying. So last lecture talked a lot about information flows with a little bit of mention of energy as well. But arguably sometimes I would argue that sometimes it's energy that's more predominant for the increase in complexity. So when humans discovered fire, it was a new, it's probably Homo erectus, but anyway, they had a new energy source. It wasn't so much informational, except that the information is passed on from generation to generation how to use it. But really, the primary change there is energy. So it's an interplay of many different factors, including information and energy, and other factors. The free energy rate density seems best known, again, but free energy rate density is the best metric known by our group of people. And I think in large part because he's one of the founders of Big History. But again, it's outside. If you go to Santa Fe, those people maybe some of the other institutes that study complexity, it does not seem to be in their scope of vision. Although I think it probably has utility in certain situations and for outlining general trends. But there's always a lot of counterexamples, many of which I did not have time to go into. One example was that he said Azobacter, a soil bacterium, uses 10 to the 7th units of energy. And a human riding a bicycle uses way less than that by orders of magnitude, say 10 to the 5th or 10 to the 6th, or something like that. So anyway, lots of problems with every metric, and we just have to figure out which one's going to best be used for our context and understand that there's going to be a limitation in any metrics, reliability and precision, at least with what we have so far. Thank you.